Thanks. So before I continue, thanks to feedback from audience, I can make two remarks here. I think somewhere I wrote the Q expansion of a form of weight k like this, which of course should have been like this. All right, so that's one. The other one was when I gave this motivation about removing the supersingular points from the moduli space, you should take that explanation as a bit of heuristics. It can be made precise after you remove the supersingular points, but just trying to motivate why it should be done. Okay. All right, so last time I think I ended defining overconvergent forms and the action of the UP operator. And I explained that to define the action of the UP operator, we have to overconverge the canonical subgroup. So let me write the theorem, which I will use again. So remember the section which was defined on the ordinary locus to the natural forgetful map going from the y to the x, which gave you the canonical subgroup. E and P goes to E and P and the canonical subgroup. It can be extends p-adically analytically to one, well, I'm going to call it again x, from xqp, where the valuation that I define goes from 0 up to p over p plus 1, open. To y. Okay. So remember, this was the locus where the valuation was 0, and you had a section on it, and the section extends from valuation 0 up to p over p plus 1. Okay. And furthermore, if valuation of a point is less than p over p plus 1, so it falls in this region, and there is a canonical subgroup, then for any c different from the canonical subgroup, which is the subgroup of order p, the valuation of E mod c and the image of p in that is going to be 1 over p times the valuation of EH. EP. Okay, so if you divide a point in the, let me call this the canonical locus. Okay, so if you take a point in the canonical locus and you divide that data by a subgroup which is not the canonical subgroup, the valuation will decrease, become 1 over p times the initial value. Okay. So this tells you the following. How I defined UP for you, it tells you that, UP of let me just write it. All right, so if V is less than P over P plus 1, then if you apply the UP correspondence that was only partially defined, this UP correspondence is only defined where the canonical subgroup exists. Okay, so if you take that partial correspondence, apply it to this region, it will go inside a smaller region. So in particular, it tells you that this region is, you You can think of it as stable under UP, so you can define a UP operator and on overconvergent forms and so on. But also, this is exactly why the UP operator is a compact operator on the space of overconvergent forms. This shrinking. If you take V to be 0, then you're not actually shrinking the space. But as soon as V is positive, that shrinking allows you to prove the compactness of the operator. So that was the main point of considering overconvergent forms, the way I explained for you. Okay. All right, so UP acts on MK, dagger, and it's compact. All right. Now, I want to talk about the main content of the second, this talk, which is analytic continuation. Let me call this take 1. Now, this is a result that has been known for a long time, before Buzzard and Taylor wrote this paper. But let me tell you what was lacking with this. So first of all, note that if you have two opens, V inside U, inside the canonical locus, such that the UP correspondence takes the bigger one inside the smaller one, just like over there, then if you consider a section over the smaller open of omega k, it implies that UPF is a section over the larger open. It goes in the other direction. Okay. What's that good for? Now assume that UPF equals APF. So F is an eigen vector for UP, and such that AP is different from 0. So that tells you that the functional equation F equals 1 over AP UPF implies that, in fact, this extends F from the smaller set V to the larger set U. Okay? So F is defined on the smaller set, UPF is defined on the bigger set, but UPF is essentially F. So this simple principle is behind the analytic continuation technique in Buzzard-Taylor's paper. Okay? And how does it work? Let me give you the classical result that was known always before the work of Buzzard and Taylor. So let me write corollary. If I apply that result and combine it with this, it tells me that if F is defined on okay, so like over there, V is less than P over P plus 1, and F is defined on the set valuation less than V over P, then F extends to XQP analytic up to valuation V. Okay? So just because of the corollary over there. So as long as you are before P over P plus 1, or actually, sorry, this is V over P. So as long as you're before 1 over P plus 1, you can always extend it to a larger domain. And if you keep repeating this, it proves you the following, that if you have an overconvergent modular form of weight k, such that UPF is APF and AP is non-zero, then F will automatically extend to the canonical locus. To the canonical locus, which is X QP analytic, going from 0 up to P over P plus 1 open. Okay. All right. So this is, if you study overconvergent forms, you will see that a lot of the time people just, instead of considering a particular V, always just work over this canonical locus, because it will automatically go up to that point anyway. All right. Now let's think about it. If you had occasion to use this result, and actually you wanted more analytic continuation, how would you do it? What is the picture? The picture is this. You have these supersingular disks, and you have proven that, okay, your p-adic form is already defined on the ordinary locus, and it goes a little bit inside this disk. In fact, it goes up to P over P plus 1. But there is those so-called two supersingular disks, which is everything whose valuation is at least P over P plus 1, that you can't touch. And in fact, you cannot use this method to further analytically continue these functions, because there is no UP defined outside of the canonical locus. So how would you do that? The answer is simple. Of course, you work on Y, where there is a UP defined everywhere. And the theorem of Lubin-Katz tells us that because there is a section defined on the canonical locus, there is an open in Y which is isomorphic to the canonical locus, and the sheaf omega is actually a pullback under the same map pi 1. So the sections of omega to the k downstairs is the same as the sections upstairs. So you could imagine working upstairs, and in fact the UP operator, if you reinterpret it under this, becomes the usual UP operator. Okay. So, okay, there is a chance to do it, but in order to be able to make an argument like this, you need to have some kind of evaluation to see how UP moves opens. Okay, so that's something that we need to do. And in fact, that's what Buzzard did. Yeah? So Buzzard's observation was that there is not enough room on level n for analytic continuation. If you move to level gamma naught, if you add level gamma naught p, you'll have more room. And what he did, for the first time, he defined this valuation on level gamma naught p, which then he could calculate how it changes under the UP operator. So I'm going to explain very quickly this valuation on Y. Okay, so p-adic geometry of Y QP analytic. All right. We know that there is a reduction map, just like I defined for X, from here to the special fiber of Y. And I explained for you last time what it looks like. Two components meeting exactly at supersingular points. Okay. So if you take the reduction inverse of this picture, you see there are three strata here, the supersingular ones and the two ordinary ones. So you're going to get three regions here. So this one, and the supersingular locus. Let me give them names. I guess. Remember, one of these was called the one of these was the locus where the subgroup was mu p after passage to algebraic closure. One is z mod pz. So I'm going to call the mu p the multiplicative locus, the other one the étale locus, and the supersingular ones. And their reduction inverse I'm going to call yqp multiplicative, yqp étale, and yqp supersingular. And what happens, you can now show that, in fact, because this is a transversal crossing, you can calculate and see that the reduction inverse of that is, in fact, isomorphic to an open annulus of, let's say, the radii 1 and 1 over p, just like before. So we have as many open annuli here as we have supersingular points here, and we have those two components. That's how it looks like. Now, I'm going to define a valuation here by setting it to be 0 on this side, 1 on this side, and then varying between 0 and 1 in the middle. And of course, I want to pick a parameter on each of those annuli, because, okay, so what is the annuli? Each annulus is like this. Norm x between 1 and 1 over p, which in terms of valuation is the same as saying valuation is between 0 and 1. So I want to pick a certain kind of parameter here. First of all, if you have x, a parameter, then p over x is also a parameter. But I want to choose it in such a way that when the valuation goes to 0, you go towards the multiplicative locus. So that picks one of the two. And also, you can't just pick any parameter. You have to pick a parameter from the formal geometry so that these valuations become independent of the choice of parameter. But I won't tell you exactly how, but imagine that you have a nice parameter here whose valuation goes between 0 and 1. And you define the valuation this way. This is not exactly how Buzzard defined it. The way he defined it was in terms of the valuation on x. So it was a bit of an ad hoc definition, but he was able to do that because he already knew the relationship between those valuations from the work of Lubin and Katz. But let's define it like this. All right, so valuation of R is 0 on the multiplicative locus, 1 on the étale locus, and the valuation of the parameter on the supersingular locus. There's one other thing that I want to consider, the Atkin-Lerner involution, which goes from yqp analytic to itself. It's an isomorphism, automorphism, and sends a point EPH to the quotient of this data by the subgroup in it. So E mod H P bar, and then the P torsion mod H. So that's at least on the non-cuspidal locus is given like that. So this, you can define it on the mod P picture, but it switches the multiplicative and the étale locus. And here, it also switches multiplicative and étale locus and sends a supersingular to itself. In fact, we're going to use this. In fact, it's true that the valuation of W of R is 1 minus the valuation of R. So it flips the space over onto itself. Okay. Now, a more precise version of what I just said about moving from x to y is, I can write it here in terms of these valuations. So proposition, if you have a v between 0 and strictly less than p over p plus 1, then the image of the canonical section, which was defined on the canonical locus into the YQP analytic, is exactly YQP analytic of 0 and p over p plus 1. Sorry, I mean here I want to restrict it to v, and here is v. Or essentially, I guess I could have said it differently. Under this section, the valuation downstairs and the valuation upstairs are the same. Okay. Those are two different, really different objects. I will explain a little bit what those two things are in general, okay? But those are of different natures. However, on the canonical locus, after the valuations are the same under the section. Okay, what does that tell you? So I could define. So this will be now my correct definition of the p-adic modular form. So mk p-adic is h0 of omega k over the 0 valuation part of y, and m k dagger, which is the overconvergent forms, is those sections that extend slightly into the supersingular annuli now. So YQP analytic of 0 and v, where always v is positive. So those will be the definitions, and the UP and the TP, TL, and the UL, they're all defined in the usual way on Y. Okay, so advantage is that UP is a correspondence on the whole thing. And therefore, this is what Buzzard can do and does. Now, let's represent Y in terms of the valuation. So as an interval going from 0 to 1. So here, the 0 and the 1 are the two ordinary loci, and the middle is the supersingular locus. And we've already seen, okay, so what is an overconvergent form? A p-adic form is something that's defined here. An overconvergent form is something that extends slightly into it, and we've already seen that we can go up to p over p plus 1. And then what Buzzard shows is the following, that you can do, so this is 1 minus 1 over p plus 1, and then you have, I don't know, just 1 minus 1 over p times p plus 1, 1 minus 1 over p squared times p plus 1. Like that. So if you consider those intervals, yeah, you can show that UP always takes any interval to the shifts, any interval to the one before it. So this is the p-adic dynamic of the UP operator, and it takes this particular circle of that valuation and also moves that inside. So meaning that from the principle that I wrote, you can extend everything, not only up to p over p plus 1, but all the way to here, except for, of course, 1. Yeah. So you can extend it to the entire supersingular locus. All right, what's involved? In the way that Buzzard explained it, what's involved? I think I've erased it. So there was a statement from Lubin and Katz that I wrote. I only wrote part of it, which was used here. So Lubin and Katz actually calculated the relation between the valuations upstairs and downstairs without actually having defined it. So that's exactly what allows you to calculate the dynamics of the UP operator. I'm sorry?
What is the definition of UP operator?
So this is the UP operator on level gamma 1n intersection gamma naught p, the usual one, which sends E, P, and H to formal sum of all E mod C, P bar, and H bar, where C is a subgroup of order P different from H, because you want this to make sense. Yeah. And then UP of F is the sum of is 1 over P, sum of F applied to those. Okay, so let me write down what was proven here.
Sorry, so if I take something that reduces to a supersingular curve, you're saying if I take any order P subgroup and quotient by it, and I do that many times, it moves away. Even very close, no matter how I choose the order P subgroup, it moves away. Is that what
In the supersingular annulus,
yeah.
yes.
Okay, so even though there's no canonical subgroup, it doesn't matter which one I choose, it always
Yes,
moves
it will always move. Yeah, exactly. Whereas it won't be true downstairs on X. Yeah. Exactly. Okay, so the theorem of Buzzard, which says that if F is in MK dagger, UPF is APF, and AP is non-zero, then F extends analytically to Y 0 up to 1 open, which is Y multiplicative union Y supersingular. And so this is what is used in the Buzzard-Taylor argument, as I will explain. But what I want to say is it is important to move beyond the canonical locus for that argument. That's why one really has to do this. Otherwise, it was already known and proved before. So maybe I'll draw some pictures later on so you can see why. Okay, that's page 13. All right, now I want to mention something here. That's a different interpretation of this valuation, which was done by Piloni. So he reinterpreted this valuation in terms of, well, so this is something that's defined geometrically I'm using the geometry of the modular curve, but he showed that this is the same as, or actually he defined it differently, but then you could see that they're the same. 1 minus an invariant only in terms of the subgroup. So there is a degree function. So if you have a finite flat group scheme over finite over a ring of integers in a finite extension of QP, you can associate to it a degree. The way it's done quickly is that you take the sheaf of invariant differentials, you take the global sections, that's a finite torsion module over your ring of integers. You take the elementary divisors, and you sum all the valuations of the elementary divisors. And that gives you basically some sort of a length. And this is a very nice thing because it tells you that you can calculate this valuation independently of the modular curve. And furthermore, if you use results of FARG, then you can show the following, that UP, the UP correspondence always increases degree. Now, this is independent of the modular curve. You can do it just on the level of the subgroups. And in fact, it does so strictly unless the degree is an integer. In this case, 0 or 1. So if you are in the middle of the space, like if you're here, where your degree is not integer, UP always strictly increases the degree or decreases the valuation. So that's calculated in terms of the sheaf of invariant differentials of the subgroup. So it's essentially the length of it. All right. So what does it tell you? It tells you that always, so if you restrict yourself to an affinoid, now you have to use something that I didn't talk about, but you have to use the maximum modulus principle and see that on an affinoid, like any of these, the degree to which, well, the extent to which the degree decreases has a minimum because it's a compact thing. So then you could, after applying UP finitely many times, you could always land close enough to 0 where the function is defined. Okay, so that's a very nice interpretation. The good thing about it is that in certain situations it allows you to avoid this kind of precise calculation, which is generally very difficult. Okay, so that's something to keep in mind. All right. Now I want to tell you about the proof in Buzzard and Taylor of this modularity lifting result. So the result they prove is the following. Now consider a finite extension of QP the ring of integers and the maximal ideal. Consider a continuous Galois representation like that with the following properties, that rho ramifies only at finitely many primes. That if you take rho and restrict it to the decomposition group at P, it decomposes to two characters which are unramified. So I'm going to denote by alpha and beta also as the image of Frobenius, okay, so as well as the character, and which are two characters which are distinct modulo m. Maximal ideal. And if rho bar is modular and absolutely reducible, Therefore, rho is the Galois representation attached to a modular form, which is a weight 1 and level prime to p. So there exists some n such that p, the prime p, does not, that I've fixed over there, does not divide n. All right, so this is the result of the proof. Of course, this is something that you would expect, Taylor-Weill's method to prove R equals T, but that method had a defect that did not work exactly in weight 1. Okay, so you have to do a little bit of extra argument to make it, even though these days, because Calgary and Garrity have methods that you can directly do this, but at the time, you'd have to make this extra argument. And the point is that, well, you prove an R equals T theorem when T is now a Hecke algebra, and it's fine. You can prove it essentially by proving many modularity results at weight 2 and taking a limit. And then you can specialize a weight 1, and what you get, of course, you're going to get a point on the Hecke algebra, but that's not necessarily a classical modular form, because if you have weight 1, ordinary form, overconvergent, it's not necessarily classical. So if you apply the machinery that was available at the time, what you get is you get a form, let's say, such that it has weight 1, but it's overconvergent. It was p-adic, but then because it's ordinary, it will be overconvergent. So I haven't talked about these things, but let's just assume all of this. And so, in fact, you can get two forms by switching the role of alpha and beta and defining two different deformation problems. So you're going to get an f alpha and an f beta here, such that the difference is that, of course, depending on where you put the alpha and beta, that's going to give you the UP eigenvalue. So UP of f alpha is that, and UP of f beta is beta f beta. Okay? Such that your Galois representation comes from f alpha and f beta. So you prove modularity, but only overconvergent modularity. But the nice thing is that because of the decomposability of rho restricted to dp, you get two such results.
Before alpha and beta were characters, now the numbers, so you're identifying.
I just mentioned that, yeah, I will use the same notation for alpha applied to Frobenius, beta applied to Frobenius. Okay. Maybe I should write it. Okay, now, how do we proceed from here? Let's assume the problem is solved for a moment and see what we should do. Let's assume that there is such an H and see what we can do with it. So, well, this tells you that H and F alpha and F beta, they have the same Hecke eigenvalues away from Pn. And you can imagine that what H is defined on level gamma 1n, and F alpha and F beta are p-adic modular forms, and we've learned that it's good to look at them on level gamma naught p intersection gamma 1n. That's better. So that's y, and that's x. You can imagine that this, well, before that, this H is in level gamma 1n, so it's an eigenform for Tp, not Up. The level is prime to p, but these are eigenforms for Up. So that should remind you of the situation where these are the p stabilizations of H. Okay, so basically what you do, you take H, you pull back, there are two maps here, pi 1 and pi 2. Pi 1 is the one we already looked at, which forgets the subgroup, and pi 2 is the one that quotients by the subgroup. Okay? So in fact, pi 2 equals, you first apply W when you quotient, and then you forget the subgroup. All right. So you get pi 1 upper star H and pi 2 upper star H, and you look at the span of those two, that gives you a two-dimensional space of old forms that now you can find a different basis for, which are UP eigenvalues, UP eigenforms, sorry. Okay, so take span of pi 1 upper star H and pi 2 upper star H. This is supposed to be the span of F alpha and F beta. And the difference is that these are, well, H is a TP eigenform, and F alpha and F beta are UP eigenforms. And now this is an easy exercise. To find out that what those are, what the matrix change of basis is. So this is easy exercise, that F alpha must be pi 1 upper star H minus 1 over P alpha pi 2 upper star H. And F beta must be pi 1 upper star H minus 1 over P beta pi 2 upper star. So you do that calculation. And what's the corollary? The corollary is the following, that pi 2 upper star H is alpha F alpha minus beta F beta over alpha minus beta, and pi 1 upper star, oh sorry, this is pi 1. Yeah, this is pi 1. And the pi 2 is, which is the same as W applied to pi 1 upper star H, is F alpha minus F beta over alpha minus beta. Okay, so if that's true, then I have these two statements. And what I want to show you is that if you have a star and a star, you can prove that as well. And that's not so difficult. First of all, we know what H is, yeah? H has to be this. This has the same Q expansion, except that, well, this is only partially defined for us, but that should be H. H should be the analytic continuation of this thing, yeah? If there's an answer. So I want, basically what I want to show that two things, alpha F alpha minus beta F beta extends to, well, okay, maybe I shouldn't say that yet, is classical. Of level, first of level gamma 1 n intersection gamma naught p, and second, it descends to level gamma 1. So those are the two steps. And how do Buzzer-Taylor show it? It's essentially this. Again, look at Y like this. This is 0, 1. Okay, the F alpha and F beta are overconvergent, so they start here and overconverge inside. Because they are UP eigenvalues and the eigenforms, and the eigenvalue is non-zero, by the theorem that we just explained, they extend all the way to here. So F alpha and F beta, and therefore alpha F alpha minus beta F beta is defined up to there. How about F alpha minus F beta? That's also defined in the same locus. However, now look at this. high 1 upper star h, you can, well, W is essentially an involution. You can show that. So it's essentially W applied to this. I might be missing a scalar. Yeah? Okay, so there is some scalar here, but what's correct is the following, that in fact, you know that this W of this and this must be the same from there. But W of F alpha minus F beta is defined where? W, remember, when you apply W, the degree or the valuation gets flipped. So it's going to be defined over there. So that's going to be your W of F alpha minus F beta. That's a very good point. Yeah, I mean, on the surface, it looks like you don't really have to go all the way. Yeah, you just have to go halfway through. But if you wanted to prove the gluing, then that's not enough. Yeah, so there is subtlety there, and that's why you have to go actually beyond p over p plus 1. Yeah. So if I could show that W of F alpha minus F beta is the same as alpha F alpha minus beta F beta on the middle, then I could glue these two. And then I could have a global section, a global analytic section here. And then you could invoke the p-adic analytic Galois and say that global analytic section is an algebraic section, so it's a classical modular. And then, okay, then it remains to descend it to level gamma 1, and that's a different argument. But that's the main thing. So what's involved in that? I think I prefer not to get into that because there is still something left that I want to talk about. But I'll just tell you what's involved in that calculation. Well, how do you show F alpha minus F beta equals W of F alpha minus F beta? The subtlety is that usually when you want to show the two modular forms are equal, you show they have the same Q expansion somewhere, and then you use connectivity results to say that they're equal everywhere. Yeah? But here, you want to prove that on the supersingular locus where there are no cusps. So what you do, in fact, is you switch the problem. You move to a modular curve on top of this, where you add another subgroup. So there's already EPH. You add another subgroup different from H. And you look at pi 1 and pi 2, and you pull back both of these. And then you calculate at the cusp over there. And then you see that they're equal. The Q expansion calculation uses the following relationship between the Q expansions of F alpha and F beta. And then you get something which is not exactly what you want. But when you play around with it, when you write it for all possible subgroups, for all possible auxiliary subgroups, then you can actually get the result that you want. So there's a bit of work, but the reason I mention it is that at the end of the day, it relies on Q expansion calculation and some connectivity result, which is immediate in this case, but in higher dimensional situations, proving these connectivity results can be very troublesome in general. Okay. All right, so that's essentially the argument, or the geometric part of the argument. Okay, I have about maybe 10 minutes left. So I thought that maybe I can tell you a little bit about the higher dimensional situation. As I promised, I'll look at this case of Hilbert modular surfaces. All right, so what do we sort of take from all of this? I think, as I said, results like this could also be proven differently nowadays. But the thing that you get from this is this method of analytic continuation and the potential applications that it has. For example, for proving class equality results, things like that. And there are other applications that you can get from partial analytic continuation of modular forms as well. Okay, so how do you apply this kind of analytic continuation over more general Shimura varieties? Okay, so this kind of method using the degree increasing property of UP is a very nice technique. So it allows you to get analytic continuation for free to certain parts of this space. It doesn't, however, give you the optimal results. So there are certain parts of the space that you can't get through because it's not always like a linear progression. Sometimes you have to jump from corner of the space to the other and so on. So the dynamics could be more complicated. So what I'm going to tell you is that then just results about analytic continuation and what are the optimal results one can get, let's say in the case of Hilbert modular surfaces. Okay, now I don't know, what I have is going to take more than 7 minutes, definitely. So I have to sacrifice something. So I won't talk about the mod P geometry. I'll just comment on it. So consider the case of Hilbert modular surfaces. Okay, and let's assume that there's a total, the total real field of degree 2 is such that P is inert in F. So I'm going to consider the unramified situation. If P is a split in F, the picture is very simple. It's like a product of the modular curve by itself, essentially. So the interesting case is where P is inert in F. And again, there is a YQP over there, and an XQP. So XQP is the moduli of Hilbert-Blumenthal abelian surfaces. So I'm just going to put an A and underline. So A and action of OF, and polarization and level structure prime to P. And here, I'm going to put a subgroup H, where H is, well, O is the ring of integers. So H is O stable inside the P torsion, has order P squared, and is isotropic with respect to the polarization. So that's your Y. And you want to do analytic continuation of Y. And the question is, if I have an overconvergent form defined on Y, what's the best result of analytic continuation I can get? Okay, so here, as you saw, we looked at this valuation, which allowed us to draw these pictures. So again, we could define two valuations, so V1 and V2, going from Y to 0, 1 again. And in this way, you can visualize your space as a square. All right. Now, everything that has valuation 0, 0 is going to be your multiplicative locus. Everything that has valuation 1, 1 is going to be your étale locus. And then those are the ordinary parts. The rest is non-ordinary. However, the non-ordinary locus gets more complicated. And, well, you can imagine that there are two directions in which to be non-ordinary. Okay, so there is a type. So you could be super special, for example. So you could be ordinary in both directions, or could be ordinary in one of the super singular or non-ordinary in both directions, or you could be non-ordinary in one of the directions, so on. Now, what happens is that the main trouble comes from these corners of the space. So this is evaluation 1, 0, evaluation 0, 1. Now, if you go back to that degree calculation, the problem is that here the degree is going to be integer. So that kind of principle doesn't work anymore. Okay, so you have to do something for this differently. Now, one thing that we can prove rather easily is the canonical locus. Okay, we can determine the canonical locus. And that's exactly this, not including the lines. And this is 1 over 1 minus 1 over p, 1 minus 1 over p, the lengths here. So everything inside here has a canonical subgroup. And exactly with the same argument, every overconvergent form is going to extend to the canonical locus. In fact, maybe I should have defined what an overconvergent form is. So, of course, the p-adic form is something that's defined on the multiplicative locus. And overconvergent means that it extends a little bit inside. Okay? You can always extend it to the canonical locus. But that's not so good, because even though in this diagram it looks big, it's not so big, because these two are quite big. These are, in fact, parts of the space that after you reduce mod p, you get components of the special fiber. So these are quite huge. So that doesn't tell us anything about the bad locus. But then you can show the following. You can show that there's a part of this that any overconvergent form of finite slope, meaning that the UP eigenvalue is non-zero. I've always been assuming that. So any such form extends to a part of this and over up to here. Open. And what's the partial locus here? That can be defined in terms of the reduction mod p. So if you take this reduced mod p, you're going to get a component in the special fiber of the Hilbert modular surface, and that component does not have a uniform type on it. So some points on it are superspecial, and some points are supersingular. So you have to remove the superspecial ones. So you only consider the part where the type has cardinality 1, and then you can extend to it. And then you can never go too close to the étale locus. So it's not true that f extends to the entire non-ordinary locus like in the classical case. And in fact, this is the two-dimensional case, which is not representative of the general situation. In the general situation, you are going to have many edges that are not completely covered. In fact, the correct condition would be something called the generic locus, where you specify the type to be the minimum possible type on those components. So that's going to affect some of the edges, and also there are some bad edges where you have to remove a certain circles, well, partial circles, for possibly reasons of technology, but maybe it's actually essential. Okay. So one can write down a very big region here where every modular form of overconvergent form of finite slope automatically extends to that. But that's not the entire non-ordinary locus. And I mean, if you wanted to, for example, if you wanted to do a Bowser-Taylor kind of argument on this, then of course you have to take this and apply W to it. And it wouldn't cover the entire space. However, it has the property that it would cover all but a locus which in reduction mod P will have codimension at least 2. So then you can use some kind of a kosher principle, and so that can be avoided. And then also, if you wanted to prove this kind of equality, you would have to know something about the connectivity of this space. So you would have to know, well, regions like this And actually, the intersections of like this and its W, you have to know the connected components of that. And again, for that, you'd have to pass to the special fiber. So you'd have to know very well how the special fiber looks like with respect to this evaluation picture. And that can be done. So I didn't have time to explain. I wanted to draw some pictures for you, but it will take maybe 10 minutes or so. So I think I can stop here. Yeah.